Welcome to another session on circles. We have been taking up theorems on the chords. Herein we take up a few application of those theorems. I write the first one here. It reads two chords, two equal chords actually, which are named as A, B and C, D. There is a figure given to the question as well. So once I draw the figure, it will be more helpful to understand the question. When these two equal chords are produced, they meet at a point E. Now here they say prove that BE is equal to DE and AE is given to be proved equal to CE. Now let's draw the figure first. This is the circle. There are two chords. I'll directly extend them to the point where they meet, which is called E. It says this being AB, which are two equal chords CD, which is the point of intersection is E. Now the center here is named as O. We have to now prove this BE, that means this part, equal to DE as well AE, the whole of these equal to CE. To do so, I write what is given here first. The given part is AB is equal to CD. We now know what is to be proved, that is BE equals to DE and AE equals CE. That I'm not writing, but the construction part we'll need here is to draw a perpendicular from this O to AB and another perpendicular from O to CD, and we name them as L and M. I'll draw this to be perpendicular. Herein you can write OL perpendicular to AB and OM perpendicular to CD. We'll also need one more construction while joining OE. So you can write also join OE. Let's now take up the proof here. We'll try to prove the congruency of those two triangles that's formed, which is OLE. So in triangle OLE and triangle OME, what do we get? I write here first. We get OL is equal to OM. The equal chords are equidistant from the center. Here you can write equal chords are equidistant from the center. We also know angle OLE is equal to angle OME. They both are 90 degrees. And also OE is equal to OE, means that's common. So by RHS criteria, we prove OLE triangle to be congruent to triangle OME. Once we prove the congruency by CPCT, we can say LE is equal to ME. We also know, here I write using some other color, we also know that AB is equal to CD, given to us that they are equal chords. Half of AB is also then equal to half of CD. What is half of AB? That is ALY. Perpendicular drawn from the center to the chords will be will bisect the chord. So AL will be equal to, half of that will be equal to BL rather, because we need that part, though it will also be equal to AL as well. BL, and that's equal to MD. Now this one, suppose the first equation, this being the second, let us subtract 2 from the first one, I mean the second equation from the first one. So what do we get? We get BL, we'll be writing 2 from the first one, so it is LE minus BL should be equal to ME minus MD. So LE minus BL, if you look into the figure, will be BE equals DE. That's our first proof. Now look at the proof for AE equals CE. We now know this is one, and the other one along with it, we know that AB equals CD. Now we add both of these. What do we get? We get AB plus BE will then be equal to DE plus CD. If you add both of them, you can see AE will be equal to CB. That is our second proof. So we are done with the first question. Let's move on to another one. Herein I'll draw the figure and then write up the question. That will help us, relate to the statement which I might be writing. I then draw these two chords which intersect inside the circle. I also name this as O. AB, this is CD. I now write the question here. It says if two equal chords, that means in our figure it is AB and CD of a circle, intersect within the circle. I think I missed writing the point of intersection, and let's mark it as P. Within, it is within, kindly ignore that error. Wait, what do we have to prove here? We have to now prove the following. Number one, we have to prove that the segments of the chord are equal to the corresponding segments of the other chord. Let me write down, I'll then make you show them in the figure as well. The line joining the point of intersection to the center makes equal angles with the chords. Okay. Now the given part is then the two equal chords that are A, B and C, D, that's given to us, and which intersect within the circle, that's P. We have to prove, I directly write from to prove, you can also add in that given part. The segments of the chord are equal. Oh, here I missed the two. The T should be actually here. We have to then prove AP is equal to the segment of the other chord. So AP of this AB chord will be equal to the segment CP of the other chord CD. So AP is equal to CD. And obviously there is another segment, that is DPB will be equal to then DP. This is the first one. And then the line joining the point of intersection to the center. Okay, we haven't joined them yet, this part. Yes, this is the point of intersection joined to the center that makes equal angles with the chords. Okay, we will be now proving this angle. Oh god, sorry. OP. I also have to then drop a perpendicular from this O to the chord CD as well as to the chord AB, and then we name them as L and M as well. Then we can write angle OPM to be proved equal to angle OPL as well. Now we have joined OP, we have dropped the perpendicular. How do we start the proof here? In triangle OPL and triangle OMP, what all we have? Angle OLP is equal to angle OMP. They both have been drawn perpendicular, so they are both 90 degrees. OP is visibly common in both of them, and OL will also be equal to OM. They are equidistant from the center. Equal chords, right? So by RHS, we can prove the congruency of triangle OPL with triangle OMP. Once we prove the congruency by CPCT, what do we get? By CPCT, I write, we get LP equals MP. We also get angle OPL equal to angle OPM. Right? This is this part which is now proved. Let's now move on to prove the other part. We know herein AB is equal to CD. Therefore, half of AB will also be equal to half of CD. Half of AB will be AL, because again when we are dropping a perpendicular to the chord, it bisects the chord, so L is the midpoint of AB. Similarly, M is the midpoint of CD, thereby making AL equal to CM. Now look at this one. This suppose is equation 1 and this suppose is equation 2. If we add these two equations, what we get? We get AL plus LP equals CM plus MP, thereby making AP equal to CP. This is another proof we are done with. As because now AP is equal to CP, and we now subtract BP, BP equal BP, and then C, from CP we can, I made a mistake here. I should be writing AB actually. AB minus BP, because no, I'll be writing AB minus AP. Sorry for this kind of error. I'm subtracting AB minus AP, and we'll be writing CD minus CP, because we have already proved both of them. One is given equal, AB equals given CD, and AP proved equal to CP. But then when we subtract this, I'm getting BP equal to dp. Oh, we got it. We got our next proof again. I'll just repeat as because I got a bit kind of fumbled there. I'll write AB was given equal to CD, and then we also proved AL equal to CP. So I subtracted them, AB minus AP here and CD minus CP there, thereby deriving BP equals DP. That's this proof. Hope you followed it. Thank you.